So the last chapter for Physics 106, nuclear physics. Most people enjoy this chapter because it's easy. Okay, so we're going to understand the structure and composition of the nucleus. So all we care about is the nucleus. We don't care about the electrons, orbiting the nucleus. We just care about the nucleus. Understand the forces that hold the nucleus together and under what circumstances the nucleus breaks apart. We're going to distinguish between different types of radioactive decays and compute the daughter nuclei for these decays. So we'll be talking about radioactivity. Use the concept of half-life to determine the age of a radioactive sample, like radioactive dating, and develop a basic understanding of some applications of nuclear physics and an appreciation of some of the principles of particle physics. Okay, woo! Now, why do we care? Why do we talk about nuclear physics? Well, there's many, many, many applications of nuclear physics. I'm just going to quickly just show you some of them. Okay, plant mutation breeding uses nuclear physics. Fertilizers, insect control. So here, this is called a sterile insect technique. All right, so it says mass rearing of mosquitoes takes place in special facilities. So they grow a bunch of mosquitoes. And then it says male and female mosquitoes are separated. I don't know how they do that, but anyway. Then they use ionizing radiation, which we'll talk about, is used to sterilize the males. Then the sterile male mosquitoes are released over towns or cities, where they compete with the wild males to mate with the females. These females that have mated with the sterile mosquitoes, these females lay eggs that are infertile and bear no offspring, therefore reducing the mosquito population and disease transmission. So who would have ever thought of that, right? Okay, they're used in consumer products to irradiate food, kill bacteria, to industrial tracers to see like where oil goes in an engine, or inspection and instrumentation, carbon dating, we'll talk about that, desalination, whatever, I thought there was a Z in there. Medical diagnosis, oh my gosh, they're used all over the place in medicine. Medical applications of nuclear physics, cancer, radiation treatment, right? They use radiation to kill cancer cells. Computer imaging techniques, radiocarbon dating, smoke detectors, food irradiation, I already said that. Radioactive tracers, iodine-131 is used to treat thyroid cancer, and thallium-201 can be used to determine the damage done to someone's heart by a heart attack. And there's others besides just iodine and thallium. Medical therapy, I just said that. Sterilization of medical products and supplies, nuclear-powered ships, nuclear reactors for electricity. So some people look at that and say, oh, horrible, horrible, horrible. It's all air pollution, horrible, horrible, horrible. What is that? It's steam. Okay, that's all it is steam. These are called cooling towers. They just cool high-temperature water. All right, nuclear reactors for space, hydrogen, electricity in cars, environmental tracers, water tracers. All right, and on and on and on. So it's used all over the place, okay? All right, so let's talk about our present understanding of the nucleus. So here we go. The nucleus. The nucleus is a small, dense, positive core at the center of an atom. Yeah, we knew that. Now here are some things. So, the nucleus has a certain number of protons, right? So uppercase Z is the number of protons. Everybody uses that. Chemists, physicists, right? So uppercase Z is the number of protons. Okay? Now what's a proton? A proton is a positive particle, right? It has charge plus E, right? The electron has charge minus E. The proton has charge plus E. And you can look up E in your book. And it has angular momentum a half. We call it spin a half. The neutrons, the number of neutrons is uppercase N. They couldn't use P for the number of protons because P is pressure. Uppercase P is pressure, lowercase p is momentum. So whatever reason, they use Z. Right? So uppercase N, number of neutrons. What's a neutron? It has charge 0, angular momentum, or spin a half. Now they have something called the mass number. the mass number is A. So what's that? It's just Z plus N. I mean, think of an atom. You have these tiny, the super tiny electrons which hardly have any mass orbiting the nucleus. Where's all the mass of an atom come from? It comes from the nucleus, right? The protons and neutrons have much, much, much more mass than an electron. So the mass number, where all the mass in an atom is just the number of protons and the number of neutrons. So that's A, okay? So, right? So Z, number of protons, N, number of neutrons. The mass number is just the number of protons plus the number of neutrons, okay? It's just a number. It's not, has no units, it's just a number. Okay, the nuclear radius is R. And this is supposed to really be approximately R0 times A to the 1/3. This is an experimental result, okay? You don't derive it. It's an experimental thing. So the radius is R0 times A, the number of protons plus neutrons to the 1/3 power. R0 is 1.2 Fermis. What's a Fermi? Well, some people call it a femtometer. Again, this is nuclear physics, right? Things are small. So a Fermi or a femtometer is 10 minus 15 meters. So it's really small, right? Really, really small, okay? All right, so this is kind of a big deal, right? So you use, the A is Z plus N, you use the A right there. All right, this is kind of fun. So here's a picture of an atom, and here's the nucleus. And again, so you blow up the nucleus and see protons and neutrons, right? Okay, now notice the numbers here. So a typical atom, like 10 to the minus 10. Typical nucleus, remember, look at this. So the radius is 1.2 times 10 to the minus 15 times this A to the 1/3. So, what's the typical diameter? So many times 10 to the 15th, or maybe, times 10 to the minus 14. So look, the atom is 10 to the minus 10. The nucleus is 10 to the minus 14. What's the difference between 10 to the minus 10 and 10 to the minus 14? 10 to the 4th. What's 10 to the 4th? 10,000. 10,000. Now, let's keep reading. Okay, so that means that, well, hold it. So this atom diameter is 10,000 times bigger than this nucleus. Okay? All right. This picture of an atom would need to be 10 meters in diameter if it were drawn to the same scale as the dot representing the nucleus. Okay? So just think if this is the nucleus, if you had a scale model, the atom would be 10 meters in diameter. 10 meters. That's pretty big. Okay, this is here. This is the modern atom model. Again, I don't really care about is the nucleus, right? But that's okay. Electrons are in constant motion around a nucleus. We don't care. Protons and neutrons jiggle, move within the nucleus. And quarks, remember, protons and neutrons are made of things called quarks. Quarks jiggle or move within the protons and the neutrons. Now, this is kind of like what I was saying with the 10 to the 10,000. This picture is quite distorted. If we drew the atom to scale and made protons and neutrons a centimeter in diameter, then the electrons and quarks would be less than the diameter of a hair, and the entire atom's diameter would be greater than the length of 30 football fields. So we're talking about United States football. Okay? 99.99999999999% of an atom's volume is empty space. That's incredible, right? Empty space. So think about that, all right? Okay. So, all right. Now, this is a periodic chart. Everybody knows about that from chemistry. How many protons are in carbon? Well, you just look at it, right? Carbon, 6 protons, right? 6 protons. So we would say that Z equals 6 for carbon. Okay, now, here's a book I have. It's called the Nucleides and Isotopes. Okay, look at carbon. Look at how many different carbons there are. I mean, it's carbon 20, 19, 18, 17, all the way to 6. I mean, 8. Sorry. All right? What is going on with all the carbons? I mean, remember, if it's carbon, it has 6 protons. That's what makes it carbon, right? Well, what's all this baloney? Why 8, 9, and 10 and all that? Okay, so that number there, this number represents the number of protons and neutrons. Okay, the number of protons and neutrons. So those are called isotopes. Isotopes. All right? Isotopes, you know, they have the same Z, right? Same Z. So carbon has Z equals 6, but different N. Okay? So for example, like carbon 12, which is the most abundant form of carbon, so carbon 12 has 6 protons, and 6 neutrons. Let's do carbon 8, right? Carbon 8. Carbon 8, you know, again, it's carbon, so it has Z equals 6, but the number of neutrons is only 2, right? And you can keep going, all right? So these are called isotopes. Isotopes. And you can see that, you know, all sorts of isotopes, right? And every isotope has different nuclear properties. That's why we care. Yeah, that's why we care about this. Now, see this number here? Let me show you up here. Yeah, whatever. So these numbers are, it's a weighted average. Okay, it's based on the abundances of the isotopes. Okay, so the people who developed nuclear physics and atomic physics, you know, they came up with their own mass units, and we still use them. It's just convenience, you know, just convenience. So, so the mass of carbon 12 is defined to be 12U. 12U, okay? What's a U? A U is called an atomic mass unit. Atomic mass unit. And so, I mean, here's why. I mean, you know, would you rather say this thing has a mass of 12U, or would you say, you know, 12 times 1.66 times 10 to minus 27 kilograms? Well, this is nuts, right? So you just make up your own numbers, your own units, makes life easy, okay? All right, so this is true, but I don't like it. You shouldn't either. So what did we learn in relativity? In relativity, we learned that the, right, rest mass, E0 equals mc squared, right? So let's do that. What do you say? All right. So let's put in m as one mass unit. So 1.66 times 10 minus 27 kilograms. Going to put in the speed of light, squared. All right. And then we convert it to electron volts. So I'm not going to do that because I don't have enough room. No, I'm just not going to do it. All right. So I promise you, if you convert this, because it's going to be joules, right? But if you convert it to electron volts, it's going to be 931.49 million electron volts. That's an M. Million electron volts. So therefore, you do the conversion, and you get this. So, all right? So, I mean, this was one U, right? So, I mean, this is totally true, but useless, in my opinion. This is useful, right? So, one atomic mass unit is 931.49 MeV per C squared. Okay? Because remember, you know, E0 equals mc squared. Therefore, m is E0 over c squared, right? So the mass, so 1 U is this 931.49 MeV, but then divided by c squared. So this is what we're going to use. And it's going to make our life easy, so might as well do it. Okay, so just we'll use that. So just going to remember that, right? One, and you don't memorize it. I'll put it on the equation sheet and everything. So 1U is 931.49 MeV per c squared. Okay, now we'll talk about radioactivity later on. It has to do with how stable the nucleus is. So let's look at a chart that tells us some information about nuclear stability. So this is the neutron number, uppercase N, so the number of neutrons in a nucleus. This is the proton number, Z, right? Okay, so if you just had a line where N was equal to Z, you'd get this. This is the N equals Z line. However, what do you notice? Do you see a whole lot of elements that follow the N equals Z line? No, not at all. So look, so it says the blue are stable isotopes, red are unstable, so they're radioactive, which we'll talk about later. So where do most of the stable isotopes fall? Certainly not along the N equals Z line. They fall along this line, and they call it the line of stability. Okay? So stable nuclei cluster very close to the line of stability. Unstable nuclei are in bands along both sides of the line of stability. The line of stability follows the N equals Z line for Z less than 16, right? I mean, they're pretty much the same thing right here, you know. Okay, now, how come, right? Why do stable nuclei have many more neutrons than protons, right? This is what that line indicates, right? Why do neutrons add stability to the nucleus? We have to explain that. Also, why are there no stable nuclei after Z equals 83? Why? We have to explain that too, okay? Okay, so later on we'll talk about a model of the nucleus. And if the model is any good, we have to be able to use it to explain the data. All right? So we'll do that. But before we do that, we have a long ways to go. Let's talk about something called binding energy. Okay? Binding energy. So consider a car, all right? Consider a car. We want to do an experiment. So what we're going to do is we're going to experiment number 1. We're going to measure the mass of the car. Okay, whoopee, measure the mass of a car. Okay, fine. Experiment number 2. Now we're going to completely disassemble the car. And we're not going to lose any pieces. And we're going to measure the mass of each piece. Okay? Then we're going to add up all the masses. Now, how should the results compare? Well, assuming that we didn't lose anything, you would think that the total, the sum of all the pieces should equal the mass of the car, right? That's pretty reasonable, okay? So they should be completely equal, right? Completely equal. Got it. Now, though, remember, we're talking about the nucleus. So, quantum physics and all these weird things, right, that we discussed last chapter. Okay, so now we're going to do the same experiment with a nucleus. We're going to we're going to measure the mass of the entire nucleus. Then we're going to measure the mass of each piece, the protons and neutrons in the nucleus, and then add them up. And guess what? Oh, there's the parts. Pretty cool, right? Google Images. All right. Okay. Here's what happens with a nucleus. So you measure the mass of all the individual. Oh, by the way, a proton and a neutron, it's part of the nucleus, right? And so people sometimes call them nucleons. Okay? So a proton and a neutron, since they make up the nucleus, they're called nucleons. Okay, so you measure the mass of each nucleon, each proton and neutron. You add them up, and guess what? The mass of the separated nucleons is greater than the mass of the nucleus. That's like saying if you add up all the pieces of a car, that would be greater than the mass of the car. Well, that's insane, right? Well, explain it, all right? Let's explain it. Okay, what's going on? Well, it takes energy. I mean, it's pretty simple to disassemble a car, right? You just do it, big deal. But here, there's a lot of forces which we'll talk about. There's a lot of forces that are holding these protons and neutrons together, And so the nucleus doesn't want to be disassembled, okay? And so it takes a lot of energy to break apart a nucleus into its parts. Okay, so what we're saying is that the nucleus, the bound nucleus has a much, much smaller energy than its separated parts because the nature favors small energies. So this is really what I'm trying to say. Okay, so if you want to split up a nucleus, it takes energy, all right? It takes energy. Okay, so here we go. So B now stands for the binding energy. What's that? The binding energy is the minimum energy needed to disassemble a nucleus into individual nucleons. So here's your nucleus. Here's somehow, we'll talk about it later, somehow we have some energy added to the nucleus. If this has enough energy, it's going to bust up this nucleus into the protons and the neutrons. Let's write an equation. So this is an energy equation, right? So the binding energy, what's the energy of a nucleus? mc squared. So the mass of the nucleus times c squared. What's the energy of these separated nucleons? Well, we have z, that's the number of protons, right? So we have z, which is a number, times the mass of the proton, plus n, the number of neutrons, times the mass of the neutron. So this is the mass, this is the total mass, right? Times c squared. So see, it's energy, right? But we just use equals mc squared. Okay, so that's binding energy. Now, there you go. All right, pretty nice. Okay, so if you want to calculate B, you just take this and you subtract that. Whoopee, right? There it is, right? So this is the mass of the separated nucleons. Subtract the mass of the nucleus, multiply by c squared. Ta-da! So binding energy. So you got to multiply by c squared, right? E equals mc squared. This is the mass difference. Then you multiply it by c squared. All right, that doesn't sound all that difficult, right? It's not all that challenging, Big deal. But there's a problem. There's a problem. So here's Appendix C in our book. Now remember, what we want the mass of the nucleus, and we want the mass of the separated nucleons. But then you look in the appendix, it says atomic and nuclear data. Okay, let's see, there's the Z, the element, the symbol, mass number, atomic mass. What do you mean atomic mass? Do I want the atomic mass? I don't want the atomic mass, I want the nuclear mass, right? So this table doesn't help, okay? All right, so what a bummer, But it's okay. What's the difference between the nuclear mass and the atomic mass? Well, the electrons, right? The electrons. Okay, no problem. So this is how we're going to worry about that. This is how we're going to fix this problem. Okay, so here's the equation, right? The binding energy is the mass of the protons and the neutrons minus the separated, right? Minus the mass of the nucleus. And to get it to energy, we're going to multiply it by c squared. Got it. Okay, well, but we don't know this, right? All we know is the mass of the atoms. Oh, no problem. Okay, so the mass of the separated nucleons is, now here, look at, the mass of the separated nucleons is Z times the mass of the proton plus N times the mass of the neutron, right? Yeah, right here, right? Okay, but, so let's keep, okay. So what we're going to do, though, instead of saying the mass of the proton, we're going to say the mass of a hydrogen. Why do you want to do that? Because what's the mass of a hydrogen? Well, it's hydrogen, a proton and an electron. So see here, we're adding the mass of the electrons, right? So the mass of the electron is built in here, because, again, this is the mass of the proton plus mass of electron. We multiply it by Z. Okay, well, look, you just can't go adding the mass of Z electrons unless you subtract them. So here we're adding the mass of Z electrons. But what are we doing here? What's the difference between the mass of the nucleus and mass of an atom? the electrons, right? So in other words, what I'm saying is we add the mass of the electrons here, we subtract the mass of the electrons there. So what have we done? Nothing. Why did we do that? Well, because the table gives us the mass of the atom. Okay? So that's what I mean. We don't know this, but we know that, so we just using our math. Add it, subtract it. Bingo. So that's wonderful, don't you think? Okay. And again, we want this to be energy, and we're going to use, we don't want to do this in kilograms. Good grief. Why would we want to do that, right? We want to have this in terms of U, you know? And so that means instead of putting C squared, we're going to put 931.49 MeV per U. All right? So what's going to be, so these are in terms of U, but we have the U's on the numerator, the U here's on the denominator, so we're just going to get our units of energy. Awesome. Totally awesome. Okay, so what do you say we do an example so you can see what I'm talking about? Okay, let's see. Calculate the binding energy of helium-6. Helium-6. So here's the equation, right? Okay, let's do it. So binding energy is, okay, so the first thing we want to know is the number of protons. Well, helium, what's helium? Helium is 2 protons, right? I mean, that's what makes helium helium, 2 protons. So Z, 2, helium is 2, okay? So we have so Z is 2. This is the mass of hydrogen, remember? Hydrogen is the proton plus the electron. So what's the mass of hydrogen? What's the atomic mass of hydrogen? Right there. Yeah, lots of crazy, a lot of sig figs, right? So 1.007825. And you got to keep all the sig figs. Don't round. All right, so that's Z, 2 times the mass of hydrogen right there. Then we have N. Okay, look, we're talking about helium-6, right? Helium-6. Oops. Helium-6. Well, helium has 2 protons. It's 6, so the number of neutrons is 4. Yeah? Okay? All right? So we have plus 4 times the mass of a neutron. Where's that? Neutron. Right there. All right, and then we want to subtract the mass of the atom. So helium, here's helium 3, 4, 6. So helium-6, this is the mass, minus 6.018886. Oh, this is U's, by the way. I forgot to put my units. Golly, sorry. Bad. Don't forget units. Right? Units. Okay. Then we multiply that by 931.49 MeV per U. So all the U's cancel. And I promise you, when you multiply it all out, you get 29.27 MeV. Oh, why did they show you that? I don't know. All right. Now, this is incredible. So the binding energy of a helium-6 is 29.27 million electron volts. So that's how much energy it takes to bust up a helium-6 nucleus. Now, let's compare to atomic physics. These are the energy levels of the hydrogen, right? What do you notice? 13.6 electron volts, 3.4 all electron volts, right? Big deal. Doesn't take a whole lot of energy to get rid of an electron from a hydrogen atom, right? Electron volts. How much energy does it take to bust up a nucleus? Millions of electron volts. Okay? So that's the thing. Chemistry, you know, ionizing outer electrons, electron volts. Nuclear physics, busting of nucleus, millions of electron volts. So there's a huge difference, right? Okay. All right. Here's some results. So here are the isotopes. Here are the binding energies. Again, million electron volts, right? Million electron volts. Now, do you see a pattern? So, you know, this is the A, right? This is the A, the number of protons, number of neutrons. So what do you notice? Well, you know, as A increases, the binding energy certainly increases. Is it linear? It's not linear, right? Because this is increasing much, much faster than this, okay? All right. Let's see. Do I want to quit? No. Yeah, let's quit now.